Hello, my friends, and welcome to a video lecture on periodicity. Our guiding question is, how does the periodic table help us to predict patterns and trends in the properties of elements? These are our content statements for this lecture. You are more than welcome to pause the video and read them if you want to. Otherwise, here we go. Here is a quick look at our objectives for today. We are going to review the organization of the periodic table, talking about periods and groups and families. We're going to define this idea of periodicity. We're going to talk about some periodic trends: atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, and metallic character. We're going to talk about some reactions of metal and non-metal oxides with water. We're going to wrap up with a little look at oxidation states. We are talking all about the periodic table today. It is given to us in our data booklets. It is section 7. You might want to pause the video, grab your data booklet, and add some annotations as we go through this lecture. Vocabulary related to the periodic table. Periods are these rows going across. They correlate with the valence energy level, the energy level that those outermost electrons are being added to for each of the elements in that period. That period number is also going to be the principal quantum number. We talked about this just a little bit in our lecture on electron configuration. We use the letter N to indicate that principal quantum number. So if I'm talking about sodium, that final electron going into energy level number 3, principal quantum number 3. Groups are going to be these columns here. Kind of cool about all the elements in the same column or group is that they have the same number of valence electrons. Beryllium has 2 valence electrons, magnesium has 2, calcium has 2. Beryllium's 2 valence electrons are in energy level number 2. Magnesium's 2 valence electrons are in energy level number 3. We're going to divide our periodic table up into some blocks. We talked about this also in our lecture on electron configuration. Here we have our S block. Remember that helium is actually in that S block. Jumping over here, we've got the P block. In the middle here, we've got the D block. And then our lanthanide and actinide series down here is going to be the F block. We're also going to divide the elements in the periodic table into metals, nonmetals, and metalloids. The categorization of these guys, please know, is a very human endeavor. In fact, we have some elements that are super metals, and then some are just a little bit metallish, and then we have some that are just barely not metals, and then we have some that are super not metals. So it's really more of a continuum, more of a spectrum of metal character as opposed to a super delineated, discrete categorization. I'm actually going to start with the metalloids. Metalloids are in the middle between the metals and the non-metals because they're metal-ish, but not really metals. And so, again, kind of referring back to that idea of a spectrum. Our metalloids are silicon and germanium, arsenic and antimony, tellurium and polonium. You need to know those. Memorize those, mark them in your periodic table, practice recalling that these are our 6 metalloids. Please know that other sources might list other elements as metalloids because, again, this is a spectrum. It's not a super cut and dry categorization. But for us in IB Chem, we're going to memorize these 6 elements as being our metalloids. The elements to the left are going to be our metals, and the elements to the right are going to be our non-metals. We are going to talk about some special families in the periodic table. These are just going to be groups that are extra special. We love them so much we gave them extra special names. Alkali metals are going to be the group 1 guys, except not hydrogen, because hydrogen clearly is not a metal. They're super crazy reactive. We're going to talk about what they do in water. It's kind of fun. Alkaline earth metals are going to be the group 2 guys. Transition metals are our D and F blocks. Halogens, we're going to skip all the way over to group 17. These guys have 7 valence electrons. Generally, 8 means a full octet and stable. They're only 1 away from that full octet, so they also are quite reactive. And then the noble gases, group 18. these guys do have that full octet. They all have 8 valence electrons, except for helium that only has 2, because it's in energy level number 1 that only has space for 2 electrons. These guys are inert. We say that they are inert or unreactive because they are already so stable. It would take a lot of energy to get them to add or lose electrons. They are quite non-reactive. Our topic for today was periodicity. This is defined as the study of patterns and trends of properties on the periodic table. Those trends are due to the columns, the groups, having the same numbers of valence electrons, and the periods putting those valence electrons into the same energy levels. This leads to some pretty interesting trends, patterns in these properties. We're going to look at half a dozen of them over these next couple slides. And the first of our properties is atomic radius, literally the radius of atoms, the distance from the nucleus out to the valence energy level. Atomic radius is given to us in section 10 of the data booklet. The numbers on the top are atomic radius. They're given to us in 10 to the minus 12 meters. Those are the same as picometers. Here's a weird thing. Notice that lithium is 130 picometers big, and then beryllium is only 99. What madness is that? Beryllium has more protons and more electrons than does lithium. Shouldn't beryllium be bigger? No, beryllium is smaller. Beryllium is smaller because it has more protons. Lithium only has 3 protons, whereas beryllium has 4. There is an electrostatic force of attraction between the protons in the nucleus and those electrons. Protons are positively charged. Electrons are negatively charged. They attract each other. The more protons there are, the stronger is that force of attraction on the electrons. More protons means those electrons get pulled in closer to the nucleus, which makes the radius smaller. We call this ZF, or the effective nuclear charge. So as we go across, we add more and more protons, and the atom gets smaller. The radius decreases. But what about when I go down? If I compare sodium and potassium, sodium has 11 protons and potassium has 19. 19 protons should have a stronger force of attraction on all its electrons. Potassium should be smaller, but it's not. Why? Because potassium has more energy levels. We go from sodium in energy level number 3, potassium energy level number 4. Even though we've added more protons, we've also added a whole extra energy level. And also, all of these electrons are shielding this electron from the force of attraction coming from the protons in the nucleus. When we go across a period, generally, there are always exceptions, right? Generally, we're going to get smaller and smaller because we're adding more protons, which is going to increase the force of attraction on the electrons. When we go down a period, because we are adding more and more energy levels, the whole atom is going to get bigger. Partly because the electrons are in energy levels that are farther away, and also partly because of that shielding that occurs between the protons and the valence energy levels when we start adding more and more energy levels. So quick note also, just like with the list of metalloids that we talked about a little while ago, different sources might have different numbers. And so you might be looking at this 167 compared to over here is 130. Those are not the same numbers. Different sources, different experimental methods for determining radius is going to lead to some different numbers. For us, use table 10 in the data booklet. And you can probably guess that if atomic radius is the radius of an atom, ionic radius must be the radius of an ion. Ions are atoms that have lost or gained electrons and have charges. We have cations that are positively charged because they've lost electrons. We have anions that have gained electrons and are therefore negatively charged. Ionic radii are also given to us in section 10. We're now looking at the bottom numbers, still in 10 to the minus 12 meters or picometers. And now we're also given a charge. If we look at lithium here, the atomic radius was 130. The ionic radius is quite a bit smaller. Why? Well, lithium has 3 protons in its nucleus. It has 2 electrons in energy level number 1 and 1 electron in energy level number 2. If I give it a charge of +1, that's because it lost 1 electron. It lost that guy right there in energy level number 2. What does that mean? That means that lithium still has its 3 protons, but now those 3 protons have to pull on only 2 electrons in only 1 energy level. Of course it's going to be smaller. It's down a whole energy level. Notice that beryllium is even smaller again, 45 picometers for its ionic radius. It has a charge of +2. It had 4 protons. It's going to keep those 4 protons. It had 4 electrons. When it loses 2 to have a charge of +2, we now have 4 protons and only 2 electrons in only 1 energy level. Of course, it's going to be tiny. Look at our transition metals. We're going to go here. Let's look at iron super quick. So iron definitely gets smaller. We go from 124 to 61 to 55. Wait, what? That's weird. Why do we have multiple ionic radii? Well, because iron can lose different numbers of electrons. Iron can have multiple oxidation states. We could have iron 2 that lost 2 electrons. We can have iron 3 that lost 3 electrons. So just be super careful if you're being asked for the ionic radii of some of our transition metals. Make sure that you know what is the charge of that ion. So it'll be different for those different charges. Let's look at our non-metals. So let's skip over to oxygen. So oxygen had a 64 picometer atomic radius. Its ionic radius is, oh my gosh, twice as big, 140 picometers. Why is it so much bigger? Well, oxygen has those 8 protons in its nucleus. It has 2 electrons in energy level number 1, and it started off with 1, 2, 3, 4, 5, 6 electrons in its valence energy level. If it has a charge of -2, we have added 1, 2 extra electrons. Electrons don't like each other. All of these electrons are negatively charged. Things that are negatively charged repel each other. And so these 8 protons are pulling on extra electrons that are pushing away from each other. And that's going to make these anions a little bit bigger. So this table kind of cool. The gray is the atom, the atomic radius, and the color, the pink or the blue, is showing the ion. So notice that with our metals, with our cations, we get smaller. And with our non-metals, with our anions, they get bigger. Isoelectronic species are particles that have the same electron configurations. Iso means the same or equal, and then electrons. So here we have 4 particles, 4 species that are isoelectronic. They all have electron configurations of 1s2, 2s2, 2p6. They all have 10 total electrons. It's the oxygen anion, the fluoride anion, the sodium and magnesium cations. Notice that the oxygen anion has an ionic radius of 140 picometers, and then fluoride's a little bit smaller, sodium is smaller, yet magnesium is really, really, really small. Why? If they all have the same numbers of electrons, they all have the same electron configuration, they all have the same numbers of electrons in the same energy levels, why is the magnesium cation almost half the size of oxygen? My friends, it's all about those protons. Oxygen only has 8 protons. Fluoride has 9. Sodium has 11, and magnesium has 12. 8 protons pulling on 10 electrons is not as strong a pull as is 12 protons pulling on those same 10 electrons. So this is just a really nice thought about how those protons really matter when it comes to atomic and ionic radii. We're going to kind of sort of put radii away and talk now about ionization energy, which is the minimum energy required to eject or steal an electron from an atom. We can describe it with this formula. Here we have our particle, our atom. Notice that it is in gaseous state. That's important. We're going to add some amount of energy, that ionization energy. We're going to measure ionization energy in kilojoules per mole. And what's going to happen with that energy is that we can steal that electron and we have this cation left over after that electron is taken away. First, ionization energies are given to us in section 9 of the periodic table, these top left numbers. First, ionization energy is just the energy needed to steal one electron away. I might want to steal a second electron away. That would be second ionization energy. We're just going to worry about first, though. Notice from the graph that as we go across a period, from hydrogen to helium, from lithium to neon, generally there's an increase in ionization energy. Why? Well, because we have more protons as we go across a period. From lithium to beryllium to boron to carbon on over, we have more and more protons. That's going to result in a stronger ZF, effective nuclear charge. And so those electrons are pulled more strongly by the increasing number of protons. When the protons pull more strongly, we need more energy to steal those electrons away. Makes sense. There's some weird divots though, right? What's going on here? What's going on here? How come there is not a tidier trend? Well, let's look at electron configuration super quick. So beryllium has 4 electrons. It's going to have an electron configuration of 1s2, 2s2. Boron has 1 more electron, 1s2, 2s2, 2p1. It actually requires less energy to steal this guy away from boron because it is unpaired. When we go back to beryllium, all the electrons are paired. It actually requires more energy to steal that paired electron than it does to steal the unpaired. But what's going on between nitrogen and oxygen? What's going on here? Well, nitrogen has 7 electrons. 1, 2, 3, 4, 5, 6, 7. So we could steal from nitrogen here. Oxygen, well, now I have this one paired guy. It's actually less stable to have a pair and 2 unpaireds than to have all unpaireds. And so having unpaired, unpaired, unpaired is a little bit more stable. More energy is needed to take this guy away. When I add that second electron into this orbital, it actually makes it a little bit less stable, which means it's easier to steal that electron away from oxygen. Super interesting, right? Now, what about going from neon down to sodium? Well, neon has those 10 electrons, 1s2, 2s2, 2p6. Sodium has 1 electron that is unpaired in a whole extra entire energy level. So not only is it unpaired, but also it's further away because now we're in energy level number 3 instead of energy level number 2. So ionization energy is going to increase generally as we go across because there are more protons, stronger pull on the electrons, more energy is needed to steal the electrons. Ionization energy generally is going to decrease as we go down a group because there are more energy levels, which means that the electrons are further away from the nucleus, therefore easier to steal, less energy is needed. Our next property is electron affinity. It is kind of the same but opposite ionization energy. Electron affinity is the energy that is released when a particle gains an electron. Ionization energy was the energy needed to lose an electron. We also can show electron affinity with this formula. We have our particle again in gaseous state gaining its electron, going to an ion and an anion. And then here is that electron affinity still measured in kilojoules per mole. Also given to us in table 9, it's going to be our top right number. We have electron affinity, and then second electron affinity is just going to be how much energy is released when a second electron is added. Notice from the graph that a huge amount of energy is released. Notice our big negative numbers up here when the halogens gain electrons. Let's talk about why. Fluorine's electron configuration, fluorine has 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. It is 1 electron short of having the same electron configuration as the noble gas neon. When fluorine adds that electron, it now has a full octet, and it is so crazy stable, a lot of energy is released. So when we go from fluorine with 7 valence electrons to fluoride with 8 valence electrons, and therefore a full octet, crazy more stable. And because it's more stable, it's letting go a lot of energy. Things that are very stable have low energy. So when you make something more stable, that energy is released. Notice that there are in this graph some particles that have positive electron affinities. To give argon, which is a noble gas, which is already crazy stable, to give it an extra electron is not going to make it more stable. And so it's going to have a positive electron affinity, or none at all. So in our data booklets, we just don't even give argon an electron affinity because it would not ever want, not that atoms want anything, but it's not going to be more stable with an extra electron. Ionization energy was all about losing electrons. Electron affinity was all about gaining electrons. Now we come to electronegativity, which is all about sharing electrons. So electronegativity is the measure of an atom's ability to attract a pair of shared electrons. Here we're looking at oxygen and hydrogen in a water molecule. Oxygen has an electronegativity given to us also in section 9 of the data booklet of 3.4, whereas hydrogen has only 2.2. 3.4 is greater than 2.2, and so the electrons that are being shared in this bond between oxygen and hydrogen in this water molecule are getting pulled more toward the oxygen atom than they are toward the hydrogen atoms. So even though they're sharing, they're not sharing equally. Those electrons are hanging out a little bit more with oxygen. This is the idea of electronegativity. So we're not stealing and we're not gaining, we're pulling on shared pairs of electrons. Notice that there is no unit given for electronegativity. It is a relative scale. There was a scientist, Linus Pauling. He put together a scale. He decided that because fluorine was the most electronegative, he was going to give it a 4 on the scale. And then everything else gets a number that is relative to fluorine's pull on shared electrons. The closer atoms are to fluorine, the higher their electronegativity values. The further away we get from fluorine, the lower are those electronegativity values. This graphic is really nice to summarize the trends that we have looked at already. So ionization energy increases across more protons, means more pull on the electrons, means more energy needed to steal it. Electron affinity, similar trend, more protons. We are going to get more and more stable as we add more electrons, and so electron affinity goes up. The smaller our atoms are, the fewer energy levels they have, the more stable they become when they gain electrons. Therefore, their electron affinities are higher when they are more toward the top of the periodic table, when they have fewer energy levels. Same for ionization energy. It's going to be highest at the top of the periodic table because those atoms are smaller. Fewer energy levels means that the electrons are held more tightly to the protons. More energy is needed to steal them. Atomic radius is going to get bigger as we go down the periodic table. Interestingly, it gets smaller and smaller as we go across. Our biggest atoms are going to be here. Our smallest atoms are going to be here. This idea of metals and nonmetals. The more toward that bottom corner where we have big radii and super low electron affinities and low ionization energies, the more metal character things have. Atoms that are in that top right corner are going to be the most non-metallic, except for hydrogen. We're going to kind of pretend like he's over here when it comes to metal versus non-metal character. Do remember that there are lots of exceptions. These are not perfect trends. We don't always have an increase. There might be little blips here and there. And also remember that we might have different values depending on the different sources, depending on the different methodologies that were used to determine all of these different properties. Way back at the beginning of this lecture, we talked about how alkali metals, group 1 alkali metals, are super reactive, and our halogens are super reactive, and our noble gases are not. The reactivity of alkali metals, those group 1 metals, also changes as they get bigger and bigger and bigger. So here we've tossed some lithium into water, sodium into water, potassium into water. You can see that the reactions are getting way more energetic. There's a lot more going on with the potassium than with the lithium. What's happening is that the sodium is reacting with the water to produce a hydroxide and some hydrogen gas. We actually have some sodium at school. We're going to do this demo. Super fun. Dangerous, and so we're going to put a lot of safety precautions into place. We are not going to just play for fun. We will do this safely, but it's pretty cool stuff. So get excited for that. We're going to look now at how metal oxides and non-metal oxides react with water. What are the trends in these reactions? Oxides are simply compounds that have oxygen in them, so metal oxides are metals bonded to oxygen. Non-metal oxides are nonmetals bonded to oxygen. Looking here, we have the metal sodium bonded to oxygen, so this would be a metal oxide. When I add it to water, we end up with some sodium hydroxide. Sodium hydroxide is quite basic. We would call it an alkaline solution. It's going to have a pH that is greater than 7. Same thing happens when I add my magnesium oxide, another metal oxide, to water. We're going to end up with magnesium hydroxide, another basic or alkaline solution. These metal oxides react with water to make basic or alkaline solutions. I'm going to skip aluminum. We're going to look now at our non-metal oxides. Carbon dioxide, carbon here, is a non-metal. When it reacts with water, we get H2CO3. This is carbonic acid. It's an acid, and it has pH that is less than 7. SO3, sulfur trioxide, and water react to make H2SO4, sulfuric acid. NO2, another non-metal oxide, when reacting with water, is going to give us a little bit of nitric acid and also a little bit of nitrous acid. Lots more acid, pHs of less than 7. So our metal oxides are going to react with water to make basic solutions. Our non-metal oxides are going to react with water to make acidic solutions. But what about aluminum? I skipped it. Aluminum is a metal, but interestingly, aluminum oxide does not react with water by itself. It doesn't dissolve, it doesn't react, nothing really happens. But if I add a little bit of acid or a little bit of base, then I can get a base or I can get an acid. And so we say that aluminum oxide reacting with water is amphoteric. Ampho means both, so it could react with water to be an acid, but it could also react with water to be a base. It can be both acidic or basic in this reaction, and so it's in the middle. It could be both. It's amphoteric. And we're going to wrap up with a little look at oxidation states, also known as oxidation numbers. These are really just the charges that we would expect ions of each of these elements to have. There is a pattern across the periodic table. Group 1 guys are most likely to lose 1 electron. They're going to have a charge of +1. Group 2 will have an oxidation state of +2. Transition metals are weird. We're going to skip them and jump over to boron, which is most likely to have a charge of +3, as will the other elements in boron's group. Carbon is everywhere between a +4 and a -4. Nitrogen is going to be a -3, and then a -2, a -1. And the noble gases are most often not going to have an oxidation state, not going to have a charge, because they are unlikely to gain or lose electrons. So there is a lovely pattern we can see, getting more positive and then getting more negative, and then we meet in the middle at carbon. But we definitely have some exceptions. And so we're going to do some practice, guys, over here, finding oxidation states in elements of compounds. I'm going to look at this copper chloride. Copper is here as a transition metal, and so it can have multiple oxidation states. We're going to have to figure out from the compound what is the oxidation state of this copper. So chloride is here. It's a halogen. It's most likely to have a charge of -1, which means that copper is going to have a +1 to balance out that 1 chloride. +1, -1 balance out. We end up with a neutral compound. And so this copper's oxidation state is +1. Sometimes we can also write those oxidation states as Roman numerals with a 1. Notice that the sign goes in front of the number. Here I have another copper chloride compound, but now I've got 2 chlorides. Each of them has a -1 charge, but -1 times 2 is -2. This one copper has to balance out both of those chlorides, so this copper's oxidation state is going to be +2 or Roman numeral 2. Here I've got nitrogen dioxide with a -1 charge. So if I say that this oxygen has a -2 charge, and there are 2 of them, -2 times 2 is -4. And then if I say that this nitrogen is -3, oh my gosh, that's -7. And then what is that even there? We're going to have to do things a little bit differently, my friends. This nitrogen is an exception. It is not going to have a charge of -3. I am going to look at that oxygen first. Generally, the further to the right in the periodic table, the more likely they are to keep the oxidation state that we have added to the periodic table. So here I gave oxygen's group a -2. I'm going to go ahead and give oxygen that -2. -2 times 2 is a total -4 for all of my oxygens. I want to keep an overall -1 charge, which means that my nitrogen needs to be a 3. It needs to be a +3. So if nitrogen has a +3 and these oxygens have a -4, the overall charge is going to be -1. Nitrogen's oxidation state is +3. Does that mean that nitrogen gave up 3 electrons to oxygen? It doesn't, because they're actually sharing electrons, but oxygen is sharing them more for itself than with nitrogen. And so we're going to round way up and give nitrogen a charge, an oxidation state of +3. Same thing for this species, NO3 with a -1 charge. I've got those 3 oxygens. Oxygen is more to the right in the periodic table, and so I'm going to give them all their -2 oxidation states. -2 times 3 is -6. I need to keep an overall -1 charge, which means that this nitrogen is going to have an oxidation state of +5. The oxidation state of this nitrogen is +5. Let's do SO3 with a -2 charge. This is our sulfite ion. Those 3 oxygens, because oxygen is more, I know they're in the same rightness. It's closer to fluorine, that is sulfur. So we're going to give oxygen that -2 charge first. Oxygen's -2 oxidation state times 3 is going to be a -6. Sulfur, for us to have a -2 overall charge, has to be a +4. +4 and -6 gives us that -2. The oxidation state of this sulfur is +4. Here, one more practice problem. Oxygen is still more to the right in the formula, a little bit closer to fluorine in the periodic table, and so it's going to get its -2 oxidation state first. -2 times 4 is -8. -8, I want to keep an overall -2, and so that sulfur needs to be +6. +6, -8 to give us that -2 overall. The oxidation state of sulfur is +6. It did not lose 6 electrons. It's sharing them with oxygen, but again, oxygen shares not fairly with that sulfur. And on that note, my friends, we have accomplished all of our objectives. We talked about groups and periods and families of the periodic table. We talked about this pattern of properties in elements of the periodic table. We talked about those trends, radii of atoms and ions, ionization energy, energy to lose electrons, electron affinity, energy to gain electrons, electronegativity, how well I share electrons, then metallic character, how do I react with water. Reactions of metal oxides and non-metal oxides with water gave us some bases and some acids, except for aluminum, which was weird and was amphoteric. It can be both an acid or a base depending on what else is mixed in with the solutions. And of course, we wrapped up with that look at oxidation states. Great work today, my friends.